I'm going to be chairing the session, and I'm going to be moderating the questions as we move through the presentation. Just give me 1 second while I share my screen. Can you all see my slides okay?
Yeah.
Yeah, that's
perfect. Good. So welcome once again to today's webinar. Today we're going to be talking about root cause analysis and how we use root cause analysis to target failures. My name is Jose Hernandez, and I'm the Continuous Professional Development Team Lead at the Manufacturing Skills Academy at NMIS. And today's speakers are Matthew Laskaj. He's Director at Project Engineering Management, and he's also the Chair of IMechE in Scotland. And we are also joined by Jamie Burns. He's Managing Director of Ailsa Reliability Solutions Limited. Both of them have many years of experience working on reliability engineering, and cause and effect and real cause analysis are key elements in this particular topic. So there's a lot of expertise that they have to share. Before we get started, I'm going to give a brief introduction into NMIS, but before we do that, we will go through a little bit of housekeeping. This webinar will be recorded and will be made publicly available on our YouTube channel. So if you would like to see the content again, you'll be able to have a look at this and all of the other webinars that we have recorded in the past. We have turned off your microphones and webcams to avoid background noise, but we welcome questions. If you have a burning question during the presentation, if you can use the raise hand feature, one team member will be unmuting you, and then you can ask the question during the session. The presenters have kindly agreed to accept that. If you, however, don't have a burning question and you would like to be answered at the end of the session, we have built some time. And if you put it in the chat box, then at the end of the session, we'll have built some time to answer all of your questions. At the end of the session, we'll be sending a request for feedback. So please take some time to complete the feedback form. If you have more ideas about topics that you would like us to cover in the future, or if you want to give us some enhancement opportunities, it's all about continuous improvement. So I'll talk very briefly, for those of you who don't know who we are. We are the National Manufacturing Institute of Scotland. We are a Scottish government initiative, and what we are is an industry-led international centre of manufacturing expertise. Our objective is to help the manufacturing sector to become more productive, more innovative, and skills is a key pillar of, or is a key part of that puzzle. And an example of that skills is what we're doing today. We're going to share some knowledge in a particular topic. How we're doing this? Well, we want to help increase productivity in the nation and in innovation by bringing together the excellent work that happens within the education sector. So further education and higher education institutions. We want to bring the excellent support that exists within our public sector organizations and also industry to work together to deliver transformational impact for Scotland and the UK. Our ultimate objective is to try to make Scotland and the UK global leaders in advanced manufacturing. Our organization is supported by a number of key stakeholders. So as I mentioned, we are a Scottish government-led initiative, but as you can see, there's a lot of support organizations that help us to be where we are and to support the organizations that we work with. It's worth mentioning that we are operated by the University of Strathclyde, so that's why all of our email addresses end up with strat.ac.uk. But we're here to work collaboratively with all of the universities across the UK. And finally, we are also part of Catapult, the High Value Manufacturing Catapult. We're the only Catapult center north of the border, but through this Catapult, we have access to a wide reach of capability. So we don't claim to have all of the knowledge and expertise, but if you come to us, we may be able to help you better navigate the support mechanisms and find a solution to the questions or the problems that you may have. Yes, in terms of what NMIS offer, we do a lot of collaborative research. So we work collaboratively with industry, and to unlock access to funding, and we use our technical teams to deliver quite technical solutions to our clients. We have a new facility that we just launched last year around summer. And we have a state-of-the-art manufacturing facility with a state-of-the-art manufacturing equipment. If you haven't had a chance to see NMIS, we are open for business, and if you want to come and see us, get in touch and we can organize a visit, and you can find out more about what we do. As part of this collaborative research and this equipment that we have, we can also offer some specialist technical consultancy. Our approach to skills, as we mentioned, is quite important, and we have an end-to-end view to this skills ecosystem from 5 to 75. We engage in STEM activity, and all the way to doctorate programs. So if you have a skills-related question, please get in touch, and hopefully we'll be able to help you with that. We have a membership model, and depending on the level of membership that companies enter, that unlocks certain services and products. And again, we'll be happy to answer questions if you get in touch about that. But as I mentioned, one of the unique selling points about NMIS, it's our network, and because we are really connected with the ecosystem, we are able to signpost our client organizations to the right support mechanisms. Because at the end of the day, we are a community. But in terms of NMIS, it might be difficult to understand if you have not interacted with us before. So we use this slide to help explain how we're structured. So we, under the NMIS umbrella or the NMIS group, there are a number of specialist technology centers. They are all independent, but we all work together to try to support our industry partners and customers. So our centers are the Advanced Forming Research Center, the Lightweight Manufacturing Center, the Digital Factory, the Manufacturing Skills Academy, the Digital Processing Manufacturing Center. Within the new building that launched, the Lightweight Manufacturing Center, Digital Factory, and the Manufacturing Skills Academy are located. The other two centers will have their own dedicated spaces. But as I mentioned, NMIS is more than this specialist center. We do have a huge network of collaborators, both in the industry and in the public sector and in the higher education and the further education sectors that can help support organizations. So at this point, I'm just going to hand over to Matthew, who will be covering his webinar. Matthew, is it okay if I hand over to you?
Yeah, of course, no problem. All right, thank you very much, Jose, and thank you everyone for joining. It's great to see so many people here on a Monday morning. As Jose said, my name is Matthew Laskaj, and I'm going to be talking about the root cause analysis process as part of the failure investigation bigger process. Going to be going through some of the key techniques, some example ones, but more importantly, we're going to relate it back to your problems and hopefully your workplaces. So we're going to make it as real life as we can. And by doing that, Jamie Burns has agreed to join us, who has a lot of experience in the field. Welcome, Jamie, as well.
Thanks, Matthew, and thanks, Jose, for the introduction. Yeah, really looking forward to this. We've spent a lot of time looking at root cause analysis, and as a business now, we try and catch this before it actually fails. So it's going to be good to talk about that and hopefully get some interaction with the audience that's here, that some problems that they may have had in their past or currently have in their sites, and we can talk about them. Yeah,
absolutely. And I think the key thing there is that it's about the audience's problems here. So if anyone does have any questions during the webinar, please stick up your hand and someone can unmute your microphone, and we're happy to talk about those questions as we go, or as you said, we can leave them to the end, because that's the purpose of today, is to try to get as much knowledge out there as we can for everyone. So, right, well, I guess we get started then. And if I can share my screen, which is always the first trick of the day. Hopefully you can see that one all right. So I love a good quote, and I saw this one. I was watching a TV program one day, and it says, "A boat engine is a machine, a predictable problem, easy to solve. You fail, and there is a paddle." And I think that we're all very good at finding the paddle in maintenance, in engineering, in industry. And it's about something's wrong, we jump to the solution and we try to fix it. And sometimes that doesn't help us in the long run. How can we get better at fixing that problem in the long term? That's what today's webinar is going to be about. And you might be wondering who this quote was from. Drucker talks about management, Deming talks about quality. Well, this one, I was actually watching a TV program one night and it was Hannibal Lecter. And clearly he wasn't talking about engineering when he said it, but it's the same idea is how do we make sure that we don't need the paddle in the first place if the consequence is too high or the problem keeps on persisting and we don't want it. So what about your business? What about your plant? What about your equipment? Do you focus on that paddle, trying to fix the problems, the reactive maintenance, or do you try to do something a little bit more long-term when it does fail? For me, it's all about fixing the fundamentals first. We need to get the ground sorted before we get into some of the fancier, maybe technology, maybe some better processes. So today, as I said, we're talking about the failure investigation process and how we can use root cause analysis as part of that to fix some of the bigger ones. So the high level process is plan. Define the problem and the scope, whether that's an engineering problem, whether it's a maintenance problem, or whether it's a failure or an incident. We then need to investigate the incident, get as much background information as possible, gather information from your software, from your technology, from your people, from your images, from experiences. That part is a really important step, which Jamie's going to go into in a bit more detail with some of his great videos that he's going to show us as well. Then we use root cause analysis to analyze that incident or the failure to try to figure out what the real root cause was. Obviously, we need to report our findings and implement them, put an action plan together, document, and make sure that it doesn't repeat and happen again. So the 4 steps that I generally talk about when I'm helping organizations or doing training courses is this: plan the work, investigate, analyze, and report. And as I mentioned, it's incident statement. What is the background? What is the basis? What is it costing you? Is it time? Is it production? Is it health? Is it safety? Put a plan together for the investigation. We then investigate the incident by collecting as much information as possible. And this is really important because, as Jamie's going to mention shortly, sometimes at the end of the failure, we don't have the information to collect because it's failed. Can we get information during that time if we can? Develop a timeline of what happened, what has changed, what was different, what were the conditions, what was the operating conditions at that point. Then we're going to use root cause analysis to try to find that process. So that's what we're going to be focusing on mostly for this morning. And then, obviously, I said we need to report it, make recommendations, put one person's name against it, and make sure you do it. So today, it's more of this number 3 part. What is the root cause analysis process? Something has failed. It's hurting us. Health, safety, production losses, cost. We don't want it to happen again, so we're going to devote time and effort, resources to do it. But sometimes the failure is too late to gather the information. Sometimes we need to gather that information, don't we, Jamie, as the thing is failing? How do you see that different, Jamie, from failed, trying to gather it, versus failing, trying to gather it?
Well, from years of experience of doing RCAs after something has failed, it's always more difficult because a lot of the time the failure is a consequence of something else. And trying to, if we take a piece of rotating equipment, sometimes it's in so many different pieces that trying to put all those pieces back together to actually show the jigsaw as it was can be very difficult. So one of the things that we try and do now, and we're seeing some good success on it, is actually most failures occur over time. So if you can gather data in advance, then something may still fail, but at least you can go back through the data stream and understand where it came from and where it started. But after the failures occurred, if you don't have that access to that data, it can be a long, drawn out, sometimes painful process trying to understand where the actual root cause was. The consequences are easy to see, but how they started, it can sometimes be difficult. So yeah, We'll go through the rest of the presentation because I'm going to start answering some of the things beforehand, probably.
Yeah, I think it's a really good point, though. I mean, in an extreme circumstances, you know, we've got an explosion. It's very hard to piece back together all of those parts to find out where was that starting point. In reality, things don't normally explode, but it can still be quite hard to say, well, where was the starting trigger point? What was the warning signs that maybe we can learn from the same warning signs next time, can't we?
Yeah, and one of the things that you're also doing a lot of the time, you're in these kind of scenarios, people are so busy. Every business is busy trying to make money. So you just fix the immediate concern.
Yeah.
And actually don't always get down to the root cause. So you may just be changing a machine or changing a component or changing something to get the machine back up and running. And the problem's still there. So there's a world of putting sticking plasters on cuts at the minute, but that's just down to operational kind of constraints that people have got. But again, if you've got data, you can actually get to the bottom of it and hopefully fix the actual root cause rather than just continually doing the same thing over and over.
Yeah, absolutely. And that source of that information you're talking about can actually come from a lot of different places. Everyone jumps to technology, you know, as their first solution, but it doesn't have to be technology. I know we're going to talk about technology with some of your videos because they look better than interviewing a fitter, perhaps. But you know, the operators and the technicians that are on the field, we can get so much information and so much useful knowledge out of them that, you know, as an engineer working, a reliability engineer working in the refineries, I used to spend all my days just walking around talking to the people saying, what are you noticing? Oh, that's making a noise. Ah, that always makes a noise. Don't worry about that one. But if that one makes a noise, that's when we start to worry. So, you know, gathering that baseline, I think, is really important. So stay tuned for some of those videos shortly and some of those good pictures. Thanks, Jamie.
No problem.
So you talked about having a process, how we have an actual root cause analysis process. A lot of the time we put up with those noises and the failures and things that are happening, and we only worry about them when they're broken, because that's when the production losses start, or that's when the consequences are too high. But for a better, more thorough process, we can use root cause analysis. We've got to balance the short-term fix, which is what Jamie mentioned, the reactive fix it now that's failed, versus a long-term proactive approach. And usually they've got root causes, not just symptoms at the end. The main areas that we can categorize these failures into is three. The human errors, the human causes. Somebody didn't do a task correctly. And it's not always their fault that they've not done it correctly. It could be the fact they didn't have training. It could be the fact that they had time pressures because other things were more urgent. So there's a lot of human factors, human causes that can be put into that. Then we've got the technical issues. Quite often it's the technical issues which get the blame for things, it wasn't designed right, or the technology failed, or something broke, or, you know, the process, it wasn't hooked up properly. I think technical issues are generally the symptoms, whereas the human causes are most often the root causes. And then we've got system causes. Everyone loves to blame management, don't they? Oh, it's management's fault. They didn't give us this, or they made me do that. But if we've got good processes in place, those things shouldn't occur, and maybe the technical issues and human causes. Do you hear that a lot, Jamie? Management don't let me have time to fix it, so we'll just do our best.
Yeah. They can't switch this off. We can't do that. The unavailability of machines to do maintenance is always a key one, because back to what I said, every business, especially the machines that we work on, they're not there because they look pretty. They're there because they do a job to make people money. So while they're making money, switching them off to be able to actually do maintenance sometimes properly, it's a challenge. And you're right in what you're saying, no, with regards to the people that are around these equipment regularly. They usually know what the things sound like and when they sound good and bad. So they can give some great insight into what's actually been going on. But you get it all the time. Is production isn't allowing us to do this, and operations won't allow this to happen. It's just the way of the world.
That's it. It's because production makes money and maintenance costs money. So who's going to win that argument?
100%.
So part of the failure process here, describe what happened. Why did it happen? When? How do we stop looking at the future? And we don't just come up with these processes ourselves. Quite often someone's invented something already. And in this case, there happens to be a standard for root cause analysis. So one of the standards we could use is the British European Standard 62740. And it describes the process similar to the one that I've just presented, the yellow circles earlier. So it's got quite a good model flow diagram for the root cause analysis. But along with that, it gives you selected processes and techniques that you can use to work alongside it. So there's a lot, there's like 20 or 30 or something in that list, which I'm not going to obviously show today. But here's a couple of the more popular ones that related to maintenance that it talks about. So when we're talking about hazards, we've got barrier, Swiss cheese model, systems model. There's some of the more hazard analysis, like HazOps and HazIDs. And then we've got more of the processes to investigate the faults, like the Y method, the fault tree method, Ishikawa diagrams. You can see there, there's only a selection. The two that I wanted to focus on as starting points for this morning is the Y method and the Ishikawa ones, because these are the ones that I personally have used the most and find as most popular. But we can also integrate it with technology. So some of the things Jamie's going to be mentioning shortly is vibration analysis, motion camera analysis as well. And also anything else you want to ask us on top of these topics, we're welcome. We're happy to divert. So the fact there's no hands raised yet means, Jamie, I think we can get onto some practical side of things ourselves before we get some inspiration.
Yep, go for it.
So, Jamie, question for you. Someone phones you up and says, oh, my fan's stopped working. It's got a fan and a motor and a belt drive. What's the reason? What's the cause of it? Tell us how to fix it.
Tell us how to fix it? Yeah.
What's the cause of it? What could
that's a hard
potential
one, because
causes
at this
be?
point you don't know how it's failed.
Yeah, what could have caused the failure?
You would, again, you would then start on table when we go into a minute the why. So when did it happen? Why did it happen? What data do you have, etc., etc. But there's lots of things. Could have been out of balance. It could have been a bearing failure. Could have been the motor. Has it been failed due to the mechanical element of it? Is it an electrical failure? So what's actually the situation with it just now? Will it just not start, or does it start and it's running, shaking itself around? So there's lots and lots of questions. And this is the thing with any of these types of scenarios, is there is a lot of questions, right, that have to be asked. And that then determines what that tree that you're just about to show looks like. So yeah, numerous things. And that's what, sorry, Matthew, that is what the kind of thing that we get is, oh, my fan's just failed.
Exactly. And that's what they tell you, and tell us what's wrong with it. And you're like, well, you know, like Jamie just said, we can brainstorm a whole lot of examples and we can try to throw out solutions. And that's what engineers love to do, is like, here's a problem, well, here's the solution. Well, let's go through a process, because maybe Jamie doesn't have the information. Well, I know he doesn't have the information because I give him none. So how do we actually come up with the solution? So the first example I just showed you from that standard is what we call the Ishikawa diagram. Some people don't like it. I personally think it's quite good because it's a bit more structured than the brainstorming model, where everyone just chucks out ideas, comes up with potential causes. Oh, one of them might be okay. Well, what happens if you can't think of enough causes? What if you get stuck in trying to create new ideas for that brainstorming process? So the whole idea is come up with that problem at the end, in the start here. The problem is my fan stopped working. And that's called the fishbone diagram, because it kind of looks like a fish bone, a fish skeleton. So in the head of the fish, the problem is the fan stopped. But what else could have been a cause of that? So rather than saying, oh, it could be the bearing, it could be the belt, it could be misalignment. Let's start off with the category. And the first category we're going to focus is on people. So what is a people-related cause that could have stopped my fan working? I didn't have time to go and maintain it. What is another people-related cause? Well, the person that did the maintenance didn't have the right skills. Once we've exhausted all of the people category, We then move on to the next one. For example, process. What is a process that could have stopped my working? Well, we didn't have a written procedure. We then move to our favorite one, management. How can we blame management for doing it? And as Jamie just said, didn't have time. Priorities. So I quite like the fishbone diagram, which is the next step of brainstorming, like Jamie was just doing, to get a more structured approach. Focus on a topic, put in those boxes whatever is relevant to your investigation or your example. So common ones are the 5 M's: methods, machinery, management, materials, manpower. 4 P's: places, procedures, people. If that one's not relevant to you, cross it out and don't include it. So I think it's just a bit more structured to brainstorming. But it doesn't really tell us which one of those is the root cause. It tells us what are possibilities of the root cause. So this is where we can maybe bring in other methods from our analysis. And the other one I had circled was called the why method, which is C4 in that standard. And it just gets us to ask 5 whys is a common one. I've actually seen in quite advanced manufacturing businesses that have every failure we get, we must do a 5 whys. And I've seen the documents, and it's just 5 whys to get to an answer. And because it's a tick box exercise, they just make up the best 5 whys they can think of to get to the solution they already would have come up with without making up the 5 whys, because the management processes are dictating what you must do. It's giving them no benefit for putting in the 5 whys, because what if there's 2 root causes? What if there's 3 root causes? But they've just done it because their paperwork tells us to. So the 5 whys I'm not really a fan of personally, because it's too linear. It's too one-dimensional. A better way to do it is we're going to branch out. Here's the problem. Here's a potential root cause. Here's another potential cause. And we keep on branching out. It's called a tree because it looks like the branches of a tree if we turned up on its head. And problem, fan stopped working. What is that caused by? Well, that is caused by the belt falling off. What is that caused by? Well, that is caused by the next thing. So here's a very simplified version of what a why tree might look like for the question I just asked Jamie. The problem, the fish head. The problem is the fan stopped working. Why did the fan stop working? Or what was that caused by? Well, it's not moving. The power's on, but it's not rotating. Okay, well, why is there no movement? Because the belt drive came off and it was vibrating too much. Oh, well, why was it vibrating and fall off? Because the bearing overheated. Why did the bearing overheat? Well, possibly it was overloaded because it was tensioned too much. Maybe it was used for too long, or maybe it didn't have enough lubrication. So we could potentially start to work on that. All right, well, why was there a lack of lubrication? We missed our planned maintenance. The lubrication auto loop system ran out of grease. So again, this is a very simplified version, doesn't have all of the detail and as many as we would have in full investigation. But now we've got 2 potential root causes, or maybe they're both root causes. So it's a much better version than that one-dimensional linear approach. Have you seen this one used a little bit more widely, Jamie, when you?
Yeah, that's the way that we've always did it. I've had exposure to some of the other, like the fishbone, etc. But in the sectors and all the kind of RCs that I've been involved in, probably in the last 10 years, I've used the kind of Y tree. We've usually got it up the other way because you end up with the problem, and then you've got a lot of Ys underneath, or a lot of potentials.
Yes.
Because you usually only get involved in these when it's something that's a bit difficult, something that's not glaringly obvious. And when it's not glaringly obvious, there is usually a multitude of things that it could be that you're then trying to disprove rather than prove.
Yeah, exactly. And I said it's the engineers love to go, here's the solution, just fix that and that'll sort it. Well, what if there's 2? I mean, I don't even have the management, the processes and the people potential on this one. So we may not be able to find evidence of the cause once it is failed, though. So usually we do these after the event, don't we? We wait till the thing's failed. Oh, it's cost us too much money. Somebody got injured. We've had an environmental spill to the ocean. Now we better do an investigation, and we kind of do it in retrospect. But as Jamie mentioned earlier, what if we could gather the information before the functional failure so that we can actually get a more accurate analysis rather than just after the fact? So there's some of the formal procedures, some of the systems from that root cause analysis. So how do we maybe link this back into reality? So I'm now going to hand over some analysis to Jamie's expertise or experiences. And the first one, Jamie, is balancing. This is a pretty common one, isn't it?
Yeah, well, I'll talk through it quickly, then we can show the video. So this was a client came to us and asked us if we would go and balance a fan for them. So we said, oh, why is it out of balance? Oh, we just get this done every 6 months. They're saying, well, don't know about that. I says, realistically, fans shouldn't just go out of balance. There must be something else. So we just said to him, do you want us to get to the bottom of it for you? And the same as everything. No, just come in and balance it. Right, okay, so we decided to take another technology with us as well as the balancing equipment, because we had a funny feeling that there was more than just an out of balance was the problem. So we went to site, and obviously we took our vibration analyzer and we took our balancing kit, but we also took the motion amplification camera, because a lot of the time in our experience what we found is an out of balance fan that continually goes out of balance. Back to the Y tree, could be that there's product on the fan itself. It could be that there's issues with the different alignment things, and there's lots and lots of things it could be. But one of the things we've found quite regularly is that it's down to actually something to do with the structure and bits breaking and stuff like that. So we had a rough idea before we went that there could have been something else there, so we just decided to take the kit with us just to see, and we can show you that video. So if you click on that video, please, Matthew.
Yep. The fan balance one first.
Yep.
All right. There's no sound, so I'll just play it, and you can talk over it.
Can you put it into full screen, please, Matthew?
Oh,
yeah. So I'll just kind of quickly talk over it. I'll maybe get you to pause it in a second, though, Matthew, if that's okay. Just pause it there. So the machine itself, it was actually vibrating that much that we couldn't even run it up to full speed. It was shaking itself around that much that it wouldn't get, we think the 20 hertz was as much as we actually put it up to. So we knew straight away that it wasn't just the balance, it was obviously something else that was going on there, because the levels of vibration were actually horrendous. So much so that the engineer that was on there, and who's been around lots and lots of sites and standing next to lots and lots of machines that are moving around, says that's the worst one they had been to. So the first thing we did at that point was say, right, well, we'll get the motion amplification camera on this, because there is something else going on. So this is it, just running at 20 hertz. If you just press play again, and you can see it's already rocking.
So Jamie, you said motion amplification. So this is a video camera that you're setting up, isn't it, to actually record images of what's happening?
Well, yeah. So for anyone who's not heard of motion amplification before, so what it is, it's a 2.3 megapixel camera, and each one of those pixels acts as a vibration sensor. So it takes this footage, puts it through some software, and then what we can do is we can actually pick individual points on this anywhere within the picture, and actually take some vibration spectrums. And then what the software does, takes all that away, it then puts it through the software process, and actually brings that movement to life. So for us, it's been a key piece of technology that we've used, because not everybody understands a vibration spectrum. Not everyone understands orbital plots and all these kind of things. Everybody understands what a video shows you. So it's a very, very powerful tool, especially to prove or disprove that something is going on. So as you can see there, obviously the motor's actually rocking on that bed plate, moving in all different directions. And if you just pause it there, Matthew, sorry for a second. So if you look, the little arrows here, they're called vector arrows. So that's the direction that the machine's moving in, or that point of interest is moving in. So you can see on the base, so I don't know if that's, obviously I can't see my screen, but the base at the bottom there is virtually not moving. But then the feet of the motor are moving a lot more. And then when you look at the actual drive end of the motor itself, it's moving quite significantly. So if you press play again. So if you pause that there. But what we did is we started noticing, so there had been repairs done on this base plate before. And then with using the technology, this is something you couldn't actually see with eye, but using the technology and the way that the light hits it and the fact that you can zoom right in and focus in on it, we noticed there was a crack. So if you press play again, and what you'll see is just underneath that foot, you'll see a crack there where the whole of that foot is moving off of that weld. Don't know if the audience can see that. So it's not the best picture, but you couldn't see it just by eye. So what happened was, while we were there, we got them to do a temporary repair to that weld, and we managed to get it so as we could actually balance the fan. So we managed to get it with the structure strong enough that we could actually run the motor up at full speed to actually balance it. So press play. That was the repairs to the welds, because they found a few bits that had cracked on it. As you can see now, that's it. That obviously it was 40 millimeters per second that it was moving at, and we got it down to 1.8 millimeters per second, well within the ISO standards for that machine. So if you just pause that there, please, Matthew. So that gives you an idea of the difference having a secure structure can make. But these people have been getting it balanced every 6 months and just coming out and just balancing out a problem, or trying to balance out a problem, should we say, because you're never actually going to balance out the problem. If there's a problem that exists, all you're doing is you're basically balancing it, and you're never getting it actually repaired and fixed properly. You're just going to be continually doing the same thing over and over and over. And I think there's a statement about that, isn't there? If you keep doing the same thing over and over, expecting a different outcome, it's a sign of madness. So we see madness regularly, not only within our own business, but out with it. And it's again back to the different factors. So your operational constraints, everything else that goes with it. But we are big believers in, don't just keep papering over the cracks. Let the cracks show themselves and look at what you can actually do about them. And this was a great example of that, where we could have just went in and tried, but we actually couldn't have balanced the fan anyway, because we wouldn't have been able to run it up fast enough. But it's okay just doing what people ask, right, and stuff like that. But there's also times where you have to try and kind of fight back and say, listen, let's take a wee step back, let's think, and let's go through your why tree and understand what the potential causes are. And that can sometimes be tough when you've got a lot of people screaming at you to try and get something back up and running. But I 100% agree it's the right approach.
Yeah, and this, while it's not always a crack that is to blame, quite often this is the same thing. We get something out of alignment, or vibration levels are high. Oh, well, let's fix the thing that's vibrating a lot. Well, what's causing that vibration? I worked in the refinery, and every 16 weeks we'd overhaul this one part of the process. But even though we'd replace the coupling and we'd replace the gearboxes, after about 8 weeks, they'd fail again. They're like, oh, it's because the vibration levels of the drum are too high. Well, in fact, it's because people weren't able to tighten up the bolts properly on footings, and they were shaking themselves loose too quickly. Same thing, different cause, but
we see a lot of that. Obviously, you get a lot of times where you're going round machines and they're vibrating excessively, but it's just down to things like the bolts, and they're not not the right type of washers put in. Maybe the wrong torque that's been applied to them to begin with, because these things have to be installed properly. A a lot of them are moving at quite a high speed. So so there's a lot of torsional and rotational forces that have been applied. You need to make sure you put them in right.
Yeah, oh, we laser aligned it and it still failed. The coupling must be the wrong coupling. Oh, really?
Yeah. Right, okay.
All right, you got another example, the second
Yeah,
one, I
so
think?
if you go on to the next one, the coupling failure, because this for me is a great example of using data. So this one doesn't have a video or anything like that, but this is a great example of if you gather data in advance, when something fails, you get a better idea of getting to the root cause of it. So this was a pump, and what had happened was the pump failed. I'll start on I'll go to the start of the process in a minute. But the problem was it failed. Coupling was destroyed. The shaft was bent. Both as it says there, both the motor and pump bearings had issues. So when you're looking at that after the event, you're saying, what was the thing that went first? And you'd be starting to look at, right, was it the coupling? Was it one of the bearings that went that then started the process for the coupling to go? Was it lubrication? Was it this? So you're starting that whole why tree. Whereas we've been monitoring this piece of equipment, and basically probably about 2-3 months before it said, right, there's a rotational looseness that's starting on it, and then we started the why tree before it actually failed. So we got to the stage where we can identify that the problem was the actual coupling itself. But back to the operational and production constraints that companies have on them, they couldn't actually, this was shutting down the whole line. So to be able to do this, they had to close the whole process. So what happened was we were monitoring it, we knew it was coming, and we were hoping that it could get kind of limped along to the next shutdown. Unfortunately, it failed before that, and they managed to get it fixed. But it did cost the customer 12 hours of downtime. But what it didn't cost them was another however many hours of a root cause analysis or a root cause failure analysis into why it happened. We knew why it happened before it happened, and then you can then make sure that, right, that was the reason. This is how we make sure we mitigate it going forward. And you've now put a new machine in, and you've got a lot of confidence that the same thing's not going to happen again.
Yeah, I think this is why it's important too to bring in the people who have the technical expertise, like yourselves. You know, maybe it's the technology, or maybe it's just the knowledge, but you know, the amount that can save you in the long run to getting that information as it's happening versus just local knowledge sometimes.
Yeah, no, it's I think it's always a bit of both, Matthew. So the technologies that are available in the market now are fantastic, and there's a lot of them that are now getting to the stage where they're taking a bit of the expert need out of it. But I still don't think that there is always a time where you're going to need somebody that knows what they're looking at.
Yeah, absolutely. It's how many times do you get phoned up and get asked, what technology should I buy? Because I get that one quite a lot. It's like,
Yeah.
Oh, what technology, what vibration analysis brand should I be buying? Like, well, what's it for? What are you doing? Do you know how to use it?
And who's operating it?
Yeah.
And that's one of the things as well. You get a lot of people nowadays where you can go and get certificates and things, right? So you can go and get trained up in things, but it takes a lot for the experience element of it. I mean, we've found it where, especially when you're trying to hire people, obviously, Jose's and deals with the Skills Academy. There's a difference between being certificated for something and then being actually what's the word I'm talking about? Competent.
Yeah.
So I see that there just now, and this is one of the things we're noticing quite a lot in industry as well, where a lot of the experienced people are now getting to the stage where they're kind of retiring, and there's a bit of a skills gap. So it's how we can help get the next generation of engineers to get that level of experience. And for me, this is where you can use technology to bridge a part of that gap, and then the rest of it's just going to be, unfortunately, sometimes it's as things fail, and it's as these processes take place, and that's where you learn.
Yeah, exactly.
I learned a huge amount about root cause analysis on probably the most difficult problem I've ever had to find from a failure in a piece of equipment, and it was down to a carbon brush. Right, so the carbon brush, so the threshold for a carbon brush, but seeing we had a Y tree, there must have been 30 different things that could have been an influencing factor. So I learned more about carbon brushes than I would ever like to think I was ever going to know about them on that process.
Or ever wanted to.
Yeah, I ever want to know, 100% more than I ever wanted to know. But that's where you learn about these types of things. So it's going to be great seeing the next generation of engineers coming through, and what technology, where the technology fit will be versus the actual kind of experience fit.
Yeah, no, it definitely is. I'm just looking at time, and I want to make sure we haven't had any questions yet. So I'm wondering whether people may be waiting to the end. So
I would rather see if there's any questions, Matthew, rather than going through more of these, because I'd be interested to hear if anyone's got any examples at the minute where they've either been through a root cause process, or they've got an issue that they can't seem to get to the bottom of.
Yeah, exactly. I think we've got our first question on that note, Jamie.
Yeah. Mark Manton is asking a question. Let me unmute you, Mark, and then you can ask your question.
Morning, can you hear me?
Hey,
Yes,
Mark.
we can,
Yeah,
Mark.
can you hear you, Mark?
Morning.
Nice to speak to you again.
Yes, good to see you, Matthew. Thanks very much for this morning. It's very good. Jamie, question about the that motion amplification camera you just shown.
Yep.
Is there a minimum level of vibration that would pick up? Because 6 millimeters per second sort of, you know, you want to be under that really, but if you're borderline, it would be useful to see it.
No, you can pick up very, very small vibrations. You can amplify that I think it's up to about 500 times now. So you'll pick up the slightest bit of movement, Mark, to be honest with you. So yeah, we've found things that are not really moving much at all, and then you can amplify that to show the actual what it's doing, even though you won't see it by eye. So no, you can pick up almost any movement at all with it.
Fantastic. And a bit of a cheeky question: is it an expensive thing to deploy?
It's an expensive thing to buy. That was the first thing that we bought when we started the business. So it's definitely an expensive thing to buy. Nah, to be honest with you, the value that you get from that, for the price that you pay for it as a service is nothing. So the value is huge. When you can put that there, if you're going to someone in your senior management team or something like that to say we need money to invest and try to fix this problem, when you show them one of those videos, you usually get it.
Yeah, fantastic. I do have an issue, but I won't monopolize the time. I have a bearing failure, which I'm trying to get to the bottom of. So I may well be in touch.
Mark, just reach out to us and we'll give you a hand. And if you're not local to us, we've got other people that we know that are that are across the country that can do these things. So I'm sure we'll be able to find someone that can help you.
Fantastic, thank you.
No problem.
Thank you, Mark.
Thanks, Mark.
There's another question in the comments from Andrew Gibb. He's asking about the tree, the Y tree process, and why would you still limit at 5 Ys? Is that something that you guys have a bit of background of five Ys? And
I think that the 5 Ys, ignore it. I hate it. I've seen places, like I said, I go into companies and their process is you must fill out a 5 Ys for every failure, and I have to think of 5 Ys. Well, what if there's more, or what if there's only 2? I think they put it 5 to make it not just jump to the answer. It's to give some expansion for it, but put in as many Ys as you want. If it's 2, fine. If it's 20, fine. But also branch out. Don't be afraid to explore other possibilities of what they were, because quite often it's a human error is somewhere in there, but we don't want to just blame the human for it. Usually there's reasons behind the human error. So I don't like 5 Ys. Just make it as big and expansive as you want.
Completely agree. Keep asking why until you get to the bottom of it.
Yeah, I get told that one. I asked why too much and not at work.
I was going to say to the audience, just feel free to type more questions in the chat if you have any questions. We still have a few minutes of our presenters. I have a question for Matthew and Jamie, maybe while the audience comes up with a couple of ideas. But you guys have mentioned some of the challenges that industry have, time pressures, lack of expertise, lack of funding, perhaps, to some of the technologies. But it seems like you guys are doing very good work with companies, and it seems to me that there's a cultural change that needs to happen. The perspective towards reliability engineering. Jamie, first for yourself, you know, the example that you showed us where you went back with the company with data, you know, and the videos, and will that help, do you think, to change the perspective of the company towards reliability engineering?
Yes, it does, because so there's a few things. I'll go back many moons ago. So it used to be your reliability engineer was the person that was kind of told to stay in the corner, because every time they opened their mouth they wanted to spend money, right? So I think, especially as plants are aging, what you're seeing is reliability is becoming more of a key subject. It used to be that obviously production always ruled the roost, but people are realizing now that they need to, the capex spend isn't there anymore to go and just buy big new fancy pieces of equipment. So they're trying to keep all their older aging plant running and still getting the same production out of it. And the only way you're going to be able to do that is by having a focus on reliability. And the only way that you can do that properly is by having a focus on data. So we're now seeing that data is becoming so much more important than it probably ever was before. And I think that's for a few reasons. One, it's probably easier to get and easier to understand now than it was before. And the technologies and the different ways of getting that information are now getting more cost effective. So all of that put together, what you're finding is people are now starting to see reliability as a key pillar within their organisations now. Some sectors are a bit further forward than others, I have to say, but you are seeing that the people are seeing the value in it. But being able to show, see like that, the motion amplification, Jose, being able to show that, it's back to a picture paints 1,000 words. Well, a video, I would say, paints 10,000 words, because it brings something that most people don't understand properly and gives them something they can understand. So yeah, we see a real shift in that. And then what that also does is it then starts to get management teams, operations teams, people believing in the reliability centered approach. Whereas before it was just a bunch of graphs and squiggles and stuff like that people looked at and went, too complicated, I'll leave it till later.
But I also see people, when you mention, absolutely think data is important and information is important, but it's not just from the technology we can get it. It's really got to be, you know, use the expertise of your people. They're the first line of defense. If they can't do it, then maybe bring in technology at that point. People rely on technology sometimes too much, and like you said, Jamie, you don't even understand what you're looking at on the screen. What are you going to do with it once you've got it?
Yeah, I think there's obviously a lot of the people on sites, they'll have more experience and be able to tell us about all these things. But sometimes I think back to the management part of it, the management needs something that's proof and evidence and stuff like this at times. Yeah. So it's kind of armoring the people that with the knowledge with something that they can take that's tangible, and it's not just because Jim said it's going to break. And eventually, when it does break, they'll say we should have listened to Jim. Right, but it's trying to arm Jim with the right kind of the right data stream, however means that is for the reporting element, to make sure that people can take it on board.
Perfect. I don't think there's any more questions from the audience, but I do have one more, which you guys have highlighted the importance of following a structured process when trying to get to your root cause. And I think some of the frustrations and my own experience in this area is, you know, we spend a lot of time building very detailed root cause analysis diagrams, only to cherry pick a few of the areas in that tree because they're the convenient ones to look at. I was wondering if you have any suggestions, you know, in terms of, you know, if or how would you approach a problem like that? Because you're right, you know, when you have a huge spider diagram and time is limited and information is not available, people do tend to take shortcuts.
I think it. I'm just saying that you're asking that. I'm just going to put it back to the last slide here on the screen. Here is, I think you said it's a process. And we've got the high-level process, which is the full failure investigation, whether that's plan, investigate, analyze, report, or maybe we're talking about today was just the analyze part. And your question was more about the root cause analysis diagram, the tree diagram or Y diagram, you know. But number one, this just reinforces exactly what just Jamie said. We need to gather information first. That's your starting point. Firstly, is the investigation worth spending our time doing in the first place? Or is it just someone's yelling about it and they're annoyed about it? So have a trigger for when you're going to do an RCE or not do one. That's what I would start at. If your trigger has now been reached, that the money is high or the safety is high, gather the information. And then we do step 2, you just mentioned the causal factor, identifying whether it's a fishbone, whether it's a Y diagram, branch it out into enough root causes that you can maybe then go and investigate further. Maybe some of them weren't valid. Maybe then we can narrow it down. So sometimes you can do that Y diagram in 2 or 3 steps. Do your high level one first, go and gather more information because we found we're actually lacking. Come back and do it again and revise it, add them in, cross them off. That's what I would do typically. Then come up with the recommendations and things like that.
So we have one more question from Thomas Ritchie, looking at the type of data that you're looking for and you know where to obtain it. You know, so how would you go about trying to look at a problem from a data perspective?
Jamie, do you want to jump in with that one?
I'll come in there. So who's that from? Thomas. Thanks for the question, Thomas. So it depends on what your failure is. So if you're doing it, so let's say you're picking up beforehand. So you may have a data stream and you're identifying that a problem is developing. That might be vibration, it may be partial discharge. There could be lots of things in what you're finding, and then starting to trend that. So you've already got that data set at the beginning, and then what you're doing is then trying to understand all of the why. So why would that be coming at that stage? If it's already after the event, then what you're looking at is what the actual problem is, so what happened, and then you're looking at what is so you're going down the why tree. What are all the things that could have took place to amount for that problem to happen, and then how you then gather potential data on that. So it may be, for example, you've got a failure of a piece of equipment, and that piece of equipment's actually got data that's running through into a DCS system or something like that. Then you'd be saying, right, so what was the electrical data on that? Do we have mechanical data? What was the last time a preventive maintenance check was carried out? Is there any other telemetry or something on it? What was the operator? Who's the person that usually operates it? All of these types of things, and depending on what you think the potential contributing factors would be, is then where you would start to try and find that data from.
Perfect. Thank you very much, Jamie and Thomas. Answers. Well, I think we're getting close to the end of the session, and it's worth mentioning that if you guys are more interested in finding more about how you can progress with your own reliability engineering, we're working together in NMIS with Matthew and he's helping us to run some training programs through the Manufacturing Skills Academy. So on the slide here, you can see some of the future activity that we're planning. So please look at this and get in touch with us if you would like to find out more about what's going to be covered in the courses. But
Matthew, we can also do them directly to companies as well. If you're have a problem, whether it's root cause analysis, whether it's, the first one's just about general strategy and fundamentals. Through the NMIS, we can work together. We're members of the NMIS, so we can help work. So same as Jamie, if you need anything.
So as we mentioned, we have that network. So yeah, please connect with us. So Matthew, thank you very much. He has the links here that you can get in touch with Jamie, with Matthew, and ourselves in NMIS. But we are at the end of the session. So thank you very much to Jamie and Matthew for presenting. I think very insightful, very useful webinar.
Can I just add one thing before we go?
Yes, of course, Jamie. Of course, yes.
For anyone that's on the call that hasn't been to NMIS's place just at the back of Glasgow Airport, I highly recommend it. The factory is fantastic, and what NMIS are trying to do for the manufacturing sector across Scotland is amazing. And I'm not just saying that because I'm here and I'm not getting paid to say that. I'm saying it because I actually believe in it. And yeah, I highly recommend taking a trip over there and seeing some of the new innovative things that are taking place and the approaches they're trying to take to the sector.
Digital factory, #digital factory, isn't it, Jose?
Yeah. No, and also the DPMC when it comes. The DPMC when it starts as well, that's going to be fantastic also.
Perfect. No, that's a good shout. Thank you very much, Jamie.
Thanks everyone for joining in. Questions.
Thanks for joining, everybody.
Thank you, everyone.
Bye.
Thank you. Bye.